Alright, so in this particular video we have a stack block system that's composed of two blocks. Here, the 3 kilograms on the bottom, and then the 2 kilogram block is on the top. And the coefficient of friction between the top and the bottom block is given as 0.4. The coefficient of friction between the surface and the bottom block is given as 0.5. And we have a force that's being applied to the right, which is 10 newtons, so the bottom block is being pulled to the right. Excuse me. Part A asks us to find the friction force that's acting on the upper block. So as you look at this particular diagram, the force that's being applied to the system is on the bottom block. So whether this 2 kilogram block moves or not is because of the frictional force that exists between the bottom and the top block. Okay. So in order to find the friction force that acts on the upper block, we have to figure out whether the system is moving first or not. Well, to figure out if the system is moving or not, we have to figure out how much force friction is exerting by the surface onto the system here. So my orange arrow here represents the force of friction that exists between the surface onto the system. So I'm just going to call this orange arrow F of fric. I don't know if it's static or if it's kinetic, so therefore I won't use the subscript S or F yet. But what I can do is I can find this force of friction. Okay. Well, to find the force of friction, all I have to do is do the coefficient of friction times the norm force that's acting on that relative surface. So if you look at the system here, the force of friction exists along the floor. So therefore, I have to account for both the masses on top of it. Okay. So this particular blue arrow represents the weight of the system. Why? Because I'm looking at the surface. Therefore, I can treat both these blocks as just one big block pressing down on the surface. So therefore, the total mass here is 5 kilograms. So the definition F of G is mass times gravity. Here, I've chosen to use 5 because I'm looking at both these blocks as just one big block pressing down onto the surface. Acceleration due to gravity is 9.8. Therefore, I know that the reaction force exerted by the floor onto the 3 kilogram block, which in this case includes the 2 kilogram, is the norm force here. But the norm force here in this particular problem, relative to this bottom surface here, is just the F of G value. So here's F of G of the system, and F of G is being pushed up by the floor, which is F of N. So therefore, I know the magnitude of F of N and F of G must be the same. So in my statement here, I can just carry down the coefficient of friction on the floor to the bottom block is 0.5. The F of N is the total mass of the system, because I'm looking at this very, very bottom floor. So therefore, I need to account for both of the masses. And I need to time that by G, which is 9.8. If I do that correctly, the force of friction here is 24.5. So the magnitude of this orange arrow is 24.5. Well, without overcomplicating it, I know that 24.5 going left is greater than 10 pulling to the right. So therefore, the force that's being applied of 10 newtons is not enough to get this system moving. Because the system's not moving, I made a conclusion here that the force of friction for the upper block is equal to 0. Oh, it's equal to 0 because it's not moving at all. So the F of friction between the upper and bottom block is a reaction force. It reacts to the system once it starts moving, but the system is not moving at all. So the top block is just chilling on top of the bottom block. So therefore, the force of friction that exists between the bottom and top block is just 0 because the system is not moving. Excuse me for my dying days here. All right, now let's do part B. Part B says if the applied force is increased to 30, so instead of 10 here, it is now increased to 30. What is the acceleration of each of the block? Well, in order to do so, we can make a quick assumption. Let's assume that there's enough friction here that keeps the system moving. So as I made a statement here, is that if the two blocks move together without slipping, I can treat the two block as just one big block. Therefore, I can just say that the F applied, which in this case is 30, not 10 anymore, minus the force of kinetic friction. Well, here I changed force of friction to kinetic friction because now I know the minimum force required to move the system is 24.5, but this statement says here is now 30, so 30 is greater than 24.5, so I know now the system is going to move. It's just a matter of will the two blocks move together or will they start slipping off relative to one another. Okay. So here I substituted F for 30 newtons, f of k is 24.5, and the mass of the system here is 5. So I'm treating the system as 1. So if it were to move, what would the acceleration be if they were to move together? So if I take 30 minus 24.5, I get 5.5, and to get a by itself, I need to divide both sides by 5. So that's 5. The 5 is in the denominator. So therefore, the acceleration of the system, if they were to move together, would be 1.1 meters per second squared. However, well, in order to find out the acceleration in the top block, I need to figure out what it actually can handle. Okay, so in this particular statement, this is the acceleration of the system if they were to move together. Well, how do I know if they move together? I can run a quick test. Well, the force of friction between the bottom and top block exists. So therefore, I'm going to draw two arrows, one pointing left, one pointing right. The top block resists the change for the bottom block, but at the same time, the top block is moving because this force of friction pointing to the right. So the block on top only has one motion possible, and that's to the right. Therefore, I can say that the force of friction exerting between the two surfaces will cause the 2 kilogram block on the top to accelerate. So I can make this statement for the top block. The force of friction is equal to mass of the top times the acceleration of the top block. Okay. Well, I can find the acceleration of the top block. Well, I can simply expand F of friction into mu, the coefficient of friction, times the mass of the top block times g. That equals the mass of the top blocks times the acceleration of the top block. Well, by doing so, I know that here mass on the top cancels out because it appears on both sides. So to find the acceleration of the top block, I can just times mu and g together. Well, mu is given in the diagram as 0.4, and then 0.4 times 9.8 is 3.92. However, this acceleration here is what the top blocks can handle. Okay, so it's important that as you find these values, you understand what this means. 3.92 is the maximum acceleration that the top blocks can handle based on the coefficient of friction given here. Therefore, I made the statement. This is the maximum acceleration that the top block can handle. Well, it can handle up to 3.92. However, the acceleration in the system is only 1.1. So therefore, I would conclude that the top block accelerates with the bottom block at a rate of 1.1 because it can handle up to 3.92, but the force of friction on the bottom only slows it down by a little bit, causing the system to be able to accelerate at a rate of 1.1. Well, 1.1 is less than 3.92, so therefore I can make a conclusion that A1 is equal to A2. So both these blocks will accelerate at the same rate, which of 1.1. Alright, I hope that helps. Stay nerdy, don't be whack.